I've been asked by a surprising amount of people how to do gecko codes and other assembly-related stuff for Return to Dreamland and kind of Wii games in general, because if you can do this for one Wii game, you can more or less do it for all. And so there's a lot of complicated stuff. I did doing a basic overview that will at least give you enough knowledge to make some basic codes will benefit the modding community a lot. There's a lot of other resources for modding the Wii and just PowerPC modding in general out there. So if you don't think what I'm saying here is enough, you can always search for more stuff on your own. So let's start with the basics. What is assembler? If I wanted to be quick, I would just say it's the compiled code, but I have seen a lot of people getting confused, especially when it comes to Return to Dreamland, because Return to Dreamland also has this interpreted language called mean. And the issue with mean is that even though yes, you technically can say you compile it, that compiles into bytecode, which I'm very quickly going to explain the difference here. When you have programming languages such as C++, how these languages work is that you do the code, and then you have a compiler. And depending on which compiler you have and the settings of the compiler, it will make the code for different computers, and in this case also for the Wii, like the Wii is a computer and all of that. And then you have interpreted languages. Interpreted languages have become very popular recently and all of that, so if you have very basic knowledge with programming, it is very likely it is with interpreted languages. And what these interpreted languages do is that they create bytecode. And then there's another program that creates the bytecode with a parser. Sometimes I heard that Python has a parser, which sounds very inefficient, but anyways, sometimes a parser or another program reads the bytecode, and then that program is designed to work on multiple different computers, so you don't have to compile multiple times, and there's a bunch of reasons why people use it. But what we're going to talk about is this, which is an actually compiled program that actually runs in the machine itself. So the way assembler works is that after it compiles, it results in machine code. But the machine code, how to explain this briefly? What the machine code is pretty much is a series of instructions that the machine reads. And it's pretty much readable in actual machine code form. We can turn that into what we call assembler, which, let me get this again, is these are your instructions we see here. I'm going to talk about what this is later on, but these are the instructions. So what we can do is, I don't know what the exact name for it is, but we can pretty much get the actual machine code and turn it into these technically humanly readable instructions. And with that we can do a lot of stuff with the game. Another reason I have seen a lot of people confuse this is that bytecode can be very similar to assembler. So let me give you an example here. Because this is kind of Kirby related, like this tutorial will help you mod Wii games in general, but it's more centered around more Return to Dreamland, because has one very special thing, which I will talk about later, but it is related to these names and colors, that makes modding this game much easier than almost any other game out there, with the exception of other games that also make the same mistake. Again, more on that later. But we see the bytecode part of here. You can see that sometimes it can be very similar to actual assembler. So here's the assembler code, and let me open here. That's the wrong window. And here we have Basil, which is the version of Mint, I guess, that HAL uses for the latest Kirby games, including the Forgotten Land. And if you see, you pretty much have a very similar structure to assembler, where you have your registers and you load stuff into them and you have functions. But there's some inherent differences. I'm not that used to Basil, so I'm gonna use the previous version, which was called Mint, which I have over here. This is for Return to Dreamland modding. And then there's a lot of similarities between this and assembler. You can see the stuff like you are setting arcs for functions, you are directly calling the function, which some from assembler do, but PowerPC doesn't. Again, this is centered around the Wii, so we are going to talk about PowerPC and not just normal assembler. And there's a lot of other stuff that makes bytecode different from assembler, even though it can be very similar. By the way, these two aren't technically bytecode. I mean, Basil may be bytecode, I don't know. But this is the compilation made by Kirby, if memory doesn't fail me, of the main language, and well, in this case Basil. And the reason it looks like this, the original version probably is closer to a more normal and conventional programming languages, but the reason it looks like this is because this was made with the information we had. And again, I'm gonna talk more on this later, but there's a reason why this one looks way more readable than this one. But again, that's later. Right now, let's get into more PowerPC specific stuff. So if you have some knowledge about the assembler, you may know that not all instructions are the same sizes. That's not the case in PowerPC. PowerPC, each instruction is the same size. I don't remember how many bytes, but I do remember each one of these occupies the same space. Which, from a working as a human perspective, it makes these games way easier to work with, from if you're doing the assembler yourself. Which is a huge advantage for modern Wii games and GameCube games, and if you want to be completionist, technically the PlayStation 3 and the Xbox 360 also have PowerPC. But they have different architecture requirements on the Wii, so there are going to be some differences. But you can basically use some of the information here to also model PowerPC stuff. So let's get into the thing itself, the instructions. They are the things you see here. So there's a lot of instructions. Pretty much there's an instruction for everything the computer can do. So you will probably with time learn the basics, like you will learn that branch link register branches to another part of the code. So like the code is read linearly, like it is this instruction, this instruction, then this one. But when there's a branch, it goes to another part of the code and reads that instead. So like, if there's actually a function to see that. If we right click this and go to follow branch, you can see that it goes to another part of the code. So how branches work is that it's read linearly, but then it sees a branch, I mean this a conditional branch, so that's okay to that. Right? It sees a branch and then it goes to the part of the code it's telling it to go, which is right here. And you will probably also know like the multiple types of branches are very important, the multiple compare instructions are very important as well, and addition and all that stuff, but you won't learn everything. And that's why we use resources. This book says most things about assembler. Then there's this book that is pretty much just the instruction set. I was looking something for a mod actually, and I was confused by the instruction, so I just searched for it, and apparently it was just a branch. And then there's the actual IBM website. If you do not know, despite the manufacturer of the console being Nintendo, they just buy chips from other companies, in this case IBM. These are the people who made the chips that we use. So like if you go to their website, you will get most of the documentation. Again, Nintendo had some like weird requirements, so there's some stuff that doesn't translate well, and the Wii doesn't use all of it. But if you want to be quick, you don't want to like sit to the entire book or F3, like here it's because we are already instructions. But if we want to search, I don't know, for example, compare word immediate. I wrote that word wrong. I forgot how to write. Compare word immediate. You see, it kind of takes a while to load. So if you don't want to take that long to search for stuff, and this is not the best method to do that, but you can just search for instructions online and just search PowerPC. The PowerPC is important because a lot of assembler instructions are named the same between multiple chipsets. So here, same example. Compare word immediate, which for those of you wondering what that is, it's literally what it says. It compares, we're gonna get more into this later on, but it compares something, that something being a word and an immediate. We will get into some terminology later on. I just want you to know that a lot of stuff is more, a lot of this stuff you can more or less tell what an instruction does just from the name. But again, if you find an instruction that you don't know what it is and you're too lazy to search it, these multiple resources, you can just search the name of the instruction, then type PowerPC. And I think this one doesn't show up, so this is a bad example. Yeah, this wasn't that. This was a good example. So let's search for one that may appear. Branch. But again, this is not the best method to do it. I highly recommend just using this book specifically, the instruction set. if you want to search what an instruction does. But apparently, Google doesn't want to help today, so this is why you don't use Brave for this. I'm used to searching this, not searching it. Apparently, Brave seems to be bad at searching assembly instructions. That was a very bad showcase of that. Ignore the screen right now. That was a very bad showcase of that. So like, let's just move on to the actual instructions. So again, you will probably have to search for most of them, especially the weird ones. But what I want for you to keep in mind is that most of these actually refer to what they do. So for example, LI means load immediate. And load means what you think. And immediate means, well, an immediate number. Sorry for the pause there, I realized that I made a mistake, so I had to call it out. So anyway, like going back to what we were talking about. Most of these instructions tell you what they do again. You will probably have to search them up when you see them. But when we say instruction like LI, it means load immediate. And immediate is just a number. So here's a good example. This 0 will be the immediate and it's loaded into register 4. Which will probably lead to a question. What's a register? And we will go into that later on, but for now, what you need to know, especially for these R's you see, is that pretty much what stores the numbers that you are using. They're similar to variables in more normal programming, but there are some differences, and I mean, more variables at the end of the day will be a register, will be a mix of register and storing stuff in memory once the code is compiled. But for now, I want to explain some stuff you can do with instructions, because once you start learning what instruction does, and again, it may be a little bit overwhelming at first, but once you start understanding and seeing the name, you will probably start getting, like, this is a very good example of that. This is SOBI. SOB, what do you think SOB means? It means subtraction, not also. I know some people probably thought we're SOB. And E, the SOBI, means immediate. So SOBI means subtract an immediate. So you are getting a value in a register, you're subtracting a set number that's set by the assembler, I mean by the code. There's also, I'm trying to search it here, there are versions of add and subtraction that are not with immediates, that just subtract and add multiple registers, but I haven't found them. Oh, this is an interesting one. This load immediate, like I said before, just putting a number into a register. Like, if you want to work with a 5 for some reason, like you want to set a value to a 5 and use it for something, you will usually use this normal load, the load immediate, with the register you want to save it in and use a 5. But then there's load shifted. This is one of the interesting things, which, do you remember how before I said that in PowerPC all instructions are of the same size? One of the kind of issues they have with architecture is that they pretty much had to split some instructions. So the register, which I'm kind of getting ahead of myself, has all the space to store a number. Remember, this is hexadecimal. I recommend trying to get somebody used to hexadecimal once you start working on this. So this is all the space a register has. But you will only be able to use 4 digits at a time, with some exceptions here and there. If you want to load if you want to use all the space to load a number completely here, you will need to use shifted instructions, like load shifted. Again, you should probably research what this instruction does yourself, but just so you get kind of a hang of it, load will usually clean what there is in the register. So when you load an immediate, when you load a word, when you load an immediate shifted, before it loads, it will make everything in the register 0, and then will load the stuff into a number. So if you want to use all the space in a register, you will either have to load this first half, or use a load shifted to load this latter half, and then you want to do an OR. It's probably an OR immediate, or ORI, how I like to call it. Because an OR is, well, if you have some knowledge on logical gates, OR is when both things are true, it passes. When any of the things you are comparing is true, it passes through even if one is false. I will only pass false when both are false. And remember, at the end of the day, this is all binary. This, even if we are representing it with hexadecimal, because, well, it's simpler to work with hexadecimal. Like, imagine how big this number would be in binary. So because of that if you want to load the other part, you can simply do an OR between the latter half of a number you want to fill and what's already in a register. So if you want to completely load a register, I'm gonna get into why you may want to when we get into register properties and other stuff. You will have to first either load or load shifted the first half of the number you want to have there, and after that you want to do an OR comparison with other parts of the number. I think I have an example over here actually. Yes, this is an example. This is from an actual code I have. So we're going to ignore a good chunk of it. So here we're loading into register 12. Here we're first loading shifted, meaning that this isn't actually 8000 because again hexadecimal, but I'm going to call it 8000 because it's easier to understand that way. And I should say 8000 or the actual number, which I'm not going to do a match here. But we're loading this into the latter half of the register. So here I should probably explain what registers are, but again, for now it's just where you store the numbers. That is explanation until we get into them properly. So that 800 will be 8000, which isn't actually 8000, will be loaded here. And then I do an ORI or immediate with the number and the latter part I want to fill. Because of how it works, is actually the same as writing this, but because I like my code to look short here, I just wrote this. But what this will pretty much do, it will load this number, which again is, remember, it's hexadecimal, so I cannot name it. It is loading this number into register 12. And I'm gonna get into why numbers that start with 8 are gonna be very important later on when we get into registers and memory and stuff. But so, just so you know, if you want to load a number into the entirety of the register, you have to do something like this. And believe me, you will probably be doing this a lot. So memorize structures like this. There's also one that's the other way around. That will be like this. I'm gonna load the same number for sake of consistency. Again, you can write it like this, or you can remove the 2 zeros because it's loading into the first part of the register anyways. And then instead of doing an ORI, you can do an ORI shifted. Load the latter part of the number that way. So these are two ways. This and this does the same. And just so you know, there are like multiple ways of handling instructions. So I know this may seem a little bit overwhelming at first, but if you give it a look and try to remember that this is pretty much just managing numbers, you will slowly get the hang of it. Before we get into the registers, there's an interesting thing with instructions. Once you're getting the hang of it, once you're starting to understand what stuff does, you will realize that you can use the instructions and gameplay and like playing at certain spots to try and figure out what each part of the code does, like not the instructions, but what a block of code does. And for that we have a very good tool. It's called breaking points. So there's an entire tab for them, but this is more for managing it. I mean, you can technically create breaking points from here, but you will usually create them from here or here. We're gonna get into memory later on. But if you wanna see what a part of code does, you can just pause it. Just put a breaking point. What a breaking point will do is that here's the managing it, by the way. Is when the code gets here, it will pause the emulation. This is why this is a tutorial specifically for Dolphin. And you can pretty much see what happens and manage the code better. At first, the use of the breaking point may seem weird. Why do I want to pause the game in specific parts of the code? There's multiple uses for it. So, as I mentioned before, CMP means compare. This is actually the instruction I showed before. This is comparing a word and a word immediate, which is pretty much comparing what's in the register that it calls it a word and an immediate, which in this case 46. So what this instruction is doing here is saying we are going to compare what is in register 0 and 46. And what it does is that it pretty much returns, I'm gonna explain the return better later on, it returns whether these two numbers are equal, whether what's here is smaller than here, or what's here is bigger than what's here. And it just returns that. It does nothing with it. Because then you have branching instructions. This is branching not equal, for example. So if the result from this is that they are not equal, and then it passes here, the instruction will branch. Remember, the code usually works linearly until it finds a branch. So if it is not equal, it will follow this branch and execute this part of the code. I just see anything like that will probably be very confusing. Because assembler can be very confusing just looking at it. Again, you kind of have to get the hang of it. But what this will allow us to do is that if you're searching a specific function, which this is why I said it is specific for return to Dreamland, I want to see what a trigger for what is, you can just go to a compare at the branch below it and pause this. And pull a breaking point here, sorry. Because you know that if the game pauses in this breaking point, it means that whatever it was comparing here, R0 was not equal to 46. And again, it may seem confusing at first, like, more than confused, to abstract at first, but if you're editing, for example, the dead subroutine, let's try to search it here, let's hope it doesn't kills. Oh wait, better, I have... Where are you, Dolphin? I have a thing here that already works with the dead subroutine. But again, I'm gonna get into how to make the codes in particular later on. But here, yeah, this is part of the dead subroutine. It's a code I made so Kirby cannot die. Good. And the code is also, for example, this is the dead subroutine, and I have another code on, so ignore that. You didn't saw that. Let's go to another red. Here. Is this a red? Yeah. So marking the names of the functions, which I'm gonna get into function stuff and why it is important for return to Dreamland specifically later on. I have said later on a lot. You can see set dead here. Like, it doesn't take a genius, you know, especially if you have some context, like here it says hero, here it says dead, here it says check. Like, usually when you say CHK, it's saying check. This is a subroutine checking if Kirby dies. You can tell that by the name. And you can see set dead here. So if you put 2 and 2 together, if this branch branches past the dead, it means that if this R0 is equal to this 0, this is not equal to this 0, sorry, this branch will not pass, it will continue a code, it will go to set dead, and it will kill Kirby. But how does it kill Kirby? Because I have experience with this subroutine specifically, I more or less know which one it does, but if you wanted to check it out, you can simply put a breaking point here, and try to kill Kirby multiple ways until it pauses the game, and that way you will be able to use breaking points to learn what this part of the code refers to each dead. That's a very strict example, I know. I'm not gonna do it because if you have seen my previous videos, my computer is kind of a potato, so if I'm recording with OBS right now, OBS and running Kirby do not go well together. So I'm not going to show it. I recommend it as an experiment, I guess. If you wanna like play with the dead subroutine as your first kind of somewhat actual gecko code, you can do it. And I recommend that. Like, I already described you a good chunk of this subroutine. Here's an address to it, specifically to a dead. So try to play with that subroutine. Like, try replicating the code I made actually, or remember, try to make it even more specifically. Try to make Kirby immune to some forms of death and not others. That's a good way to try and get it started, because that code will be simple. It will be simply ignoring a branch. I mean, not actually. Actually, no. It will be making a branch always true, so it will be replacing one of these with an always branch. So that's a fun thing you can try. Let's get into registers before explaining gecko codes properly. And as I already said, registers are pretty much what they store your information. But there are multiple types of registers, and they have a special role. So these are what we call the general purpose registers, you will be able to tell them apart because they are simply an R and a number. Similar to other programming terms, these are your basic variables. To be even more precise, they are usually equivalent to integers. That's kind of a bad way of putting it, but if you are kind of getting used to assembly, they are your closest things to integer variables. There's kind of a catch. Here's where this enters. Because due to some assembler stuff, not all the general purpose registers are used just as registers. So let's start with the simple ones and let's build up to the more complicated ones. So R13 to R31, which, if we go back here, are these registers. From here to here, they are your normal ass registers. They just store a number and the number stays there. There's a thing I want you to be careful about. Because even though there are functions in assembler, all of these registers will stay across functions. So be very careful when you are making a code, because one of these registers could be used in a later on function, and if you change it before, it may cause a crash or some other unintended behavior. I have plenty of experience with that. If you wanna, just for the sake of completion, let's go to, I don't think this subroutine does it. Let's go to our random subroutine that has it. Well, I don't want to search it because it may lag the computer a lot. Again, my computer is not the best. Oh yeah, it's kind of a little bit too much. But there's a special function called save general purpose register. I mean, like save GPR, something like that. Again, I won't say search it because this search kind of makes my computer die. But try to just find a random function that has it. But some functions do save the registers before it loads it, and then it loads the registers before the function. So like, how to explain this? Here it is actually. Save general purpose register 1. So what this function does, that it saves all the registers in memory, and then there's this function, restore general purpose register 2, which is usually run at the end of functions that saved it, to save the registers to how they were before the function was called. But even though there are some functions that do that, I highly recommend to be very careful with all the registers that are bigger than 13. Talking about being very careful with that, there's a special register that I think this doesn't mention for some reason, which is register 12, which is the volatile register. It's pretty much a register that is reset at the end of every function. We're in runtime now, apparently. Let's go back to the next routine. And R12 is very interesting. If you see the code I made, again, this is an actual code. I won't tell you what it does because it's for a project I'm working on. What I mean, this code just loads a number to memory. No, it loads a number from memory and then does something. It compares. I'm not gonna tell you why it compares. Because again, it's kind of a project I'm working on right now, and I want it to be a secret for now. But if you see, I'm using register 12 a lot here. I mean, this is not register 12, this is another thing. I'm loading into register 12 the address. I'm gonna get into that later on when we get into pointers and stuff. And then I'm loading, how to explain this. This load word is like the loads that I explained previously, but it loads directly from memory. I'm gonna explain that better later on. But what I'm doing here is I'm loading a memory location into register 12, and then I'm loading from that same memory location. You see register 12 twice here, and we're loading whatever is there into register 12, and then we compare with it. Again, I'm not gonna tell you why I did this. It's for a complicated code. I'm just gonna tell you that that's what it is. And talking about it, I forgot something important about instructions. Instructions, even though there are multiple with a lot of formats, the vast majority of them usually have a register they save stuff to. Again, this is not always the case, but the first register is usually, keyword usually, where stuff is gonna be loaded into, and then the rest is what does the operations. So load is very obvious. This load immediate, for example, it saves into register 30, and then the operation is simply loading a number. So here the number is just 0, so this just loads 0 into 30. I want to find an ADI, so an ADI is a better example of this. Here's an ADI. with the stack pointer register, which I'm gonna talk about it. We're not really gonna see it, but I'm gonna mention that it exists again. Yes. So this saves what is in the stack pointer and 24 because it's an immediate, and then it stores it into R3. And this is, for with some exceptions, the vast majority of instructions. First, there's the register where the resulting operation is going to be saved. Then there's the registers and numbers, and immediates, and whatever else it uses that actually do operations, be it, in this case, an addition. That's this one saved here. Here's a floating point subtraction, which this is an interesting one. You see that there's no I here, because this is subtraction between two registers, and I'm gonna talk about these registers later on. But here's a good example. It saves whatever happens in the floating point register 0, and then the two arguments, I guess. I mean, I don't know what referring to was a function, but the two equivalent arguments pretty much that it handles is also register 0, floating point register 0, and floating point register 31. And what this pretty much does is whatever is here is subtracted with this. And if you see, a lot of these instructions that do multiple operations, like this one, the one I showed you in my own code, they usually repeat the same register, and that's a very common thing. Because if you have a number in a register, you want to increase it by 5, for example. Let's have an example here. You want to increase what is in register 12 by 5. You will do an add with register 12. The comments are important. I'm going to talk about the tool a little bit more later on. And you want to increase whatever is in this register. How do you do that? Well, simple. You add what's already there with 5 in this case. We want to add 5 to it, and then you store it in the same register. So this simple code will add 5 to whatever is in register 12. 12 here. Again, I know I repeated this a lot, but this is very important for you to understand. Here's the operation, and here's where it's saved. Again, not all the instructions are like that. Probably the most different instruction you will use a lot is compare and branches. Compare and branches work very differently. And I think, I forgot which one it was. It was one of these, but you're never gonna edit it directly, but there's this thing called the compare register. I'm pretty sure it's this one, but I'm not sure. Which is where the result of the compare instruction, so this instruction here, is saved. You can change it for some testing, but you're probably gonna ignore it most of the time. And so what this instruction does is that it compares it, then saves the result of greater than, smaller than, equal or not equal, in a different. I think it doesn't say it's not equal actually. I think it's only greater than, smaller than, and equal, because if it's greater or smaller than, it's already not equal. So I think it only saves those 3 states. But whatever it is, it saves one of those states in a special register. So always remember, if it's a compare, it won't save anything in either of these. It's just going to compare them and store it somewhere else. But it's something like an addition, a loading instruction, and a logical gate like an or a done. It's gonna save in the first register. And for the sake of completion, the other one that doesn't save anything is branches, which will usually write like this. In the debugger of Dolphin, which if you make a shortcut for it, there's a tutorial on how to get the debugger of Dolphin, because I don't wanna waste time explaining stuff like that. But if you see the branches, it just shows you a line to where it's going. And that's very helpful. This makes the code very readable, because you know that, oh, if this condition is met, in this case, if it's equal, it will branch here, and all of that. So this is very helpful. That's not how the actual instruction looks like. How the actual instruction looks like when you are making the code is like this. A branch, and then it says the amount of lines you want to jump. That's actually a very bad example, because remember what I said before, that all the instructions are the same size? Instruction is pretty much for something long. I don't remember if it was for bytes, for words, something like that. I don't remember exactly the unit of measurement, but it was for something long. So when making a branch, you usually want to jump in sets of 4, because otherwise it will probably crash the game. So there's no 12, remember, this is assembler. Instead of 12 we have C. and this is 16. So take that into account. I don't even know which number this is anymore. I just know that this is a valid number. And like other numbers like that, this is one of the advantages of using hexadecimal. That you will be able to tell when something is a pair of 4 for a branch. If it ends in either 4, 0, 8, or see. I have a pair of 4, I meant a factor of 4, sorry. So that's the thing. And now into this actually. What am I doing here? What's this thing? This code writer master, which to my knowledge is one of the better tools that allow you to simply write assembler code and turn it into machine code. I mean, this is technically machine code, this is a Gecko code. But there are more ways of having Gecko codes. So what most Gecko codes are, I mean, not most, but the ones I'm gonna talk about, they're simply instructions. There are multiple types of codes. There's a C2 code, which basically puts multiple instructions. Here's one actually, of the same code, I think. No, this is a different code. But it creates a branch to a random empty spot in memory. I put a bunch of instructions, and then it branches back. And if we see here, these instructions are these same instructions. Remember, the point of assembler is that more or less it translates instructions directly into these instructions. So you have a direct translation between machine code instructions and these humanly readable ones. And this part is not an instruction though. This is what makes a Gecko code a Gecko code. This is what's called a C2 code, and what modes code compilers, I guess we call it a compiler. I mean, it's technically one, but not. I mean, compilers are too much. But usually you will write a code here. I will give you a C2 code, which, how to explain this? You have to give an address, which where you want the C2 code to be. And what it will make is a C2 code with the address it is putting it at, and then how many instructions it is putting. I don't remember the exacts to why it works like this, but this is actually double the amount of instructions it's putting there. And because it has to know when it ends, one of them has to be this 0, 0, 0, 0. So this 4 actually means that it is putting 8 instructions here. Which are these 8 instructions you see here? I don't know if it's the same. Yeah, it's not the same code. This is a little bit bigger. Actually, let's search for it. Yeah, here's the branch. Don't question what the code is. Are they saying? 1, 2, 3, 4, 5. Yeah. So this, it says that it's gonna put 8 instructions in a random spot of memory. It's gonna make a branch to a random spot of memory based on this address here. I'm gonna go more into memory addresses later on. And it's gonna put all of these instructions there, and then when it sees a 0, 0, 0, 0, it's gonna branch back to from whenever it branched. So this 0, 0, 0 here, it's this branch here. So going back to registers, as I said, it's not a one-to-one thing, but these are your closest things to integers. But some are different. Just I need to read some part of. These R5 to R10 are argument registers, which, if you have ever coded in a normal programming language, you are probably used to functions. You know, you pass on parameters and all of that. So usually, for the functions assembler, which you won't be able to see in all games, but with Kirby there's stuff you can do to see the functions, because Hal made a very big mistake. Hal made a very big mistake with this, and I'm gonna talk later on about that. But anyways, these registers, and I will this one too, and these are return one, I'm gonna talk about return later on, are pretty much equivalent to parameters. If you saw the save GPR function I mentioned later on, it only saved the normal use register, the save registers, how it calls it. So those are not gonna be changed most of the time, there are exceptions, but because these are considered the parameter registers. They are the registers that pass the parameters for when you call a function. So for example, you have a function for the movement of a character. And I don't know why, let's say it's like a Sonic game, where there's different speeds and all of that. Whenever you call the function to move the character, I'm oversimplifying this here a little bit, you want to be able to for it to receive different speeds, for example. So for that you want to have different parameters that can be passed to it. And where are those parameters going to be stored? Well, in the parameter registers. I mean, why am I opening all the wrong stuff? Anyways, these registers are gonna have those parameters. So these are even more dangerous to change than these ones, because these ones are not constant. These are the same across multiple functions. So then changing this can be very helpful if you know what you are doing, but be very careful with changing the registers between 4 and 10. The general purpose registers between 4 and 10. Talking about functions usually return values, but again, if you have ever worked in a programming language like C++ or even Java or other weird programming languages, you are probably used to return values. You know, return int, return boolean. That's what R3 stores in, unless it's a float function or stuff. Like if it's an int or I think even booleans in some cases. It usually works the same way, and someone's calling me when I'm recording. That's so great. Sorry there, someone was calling me. I know, very professional. But it's too long to edit, I'm sorry. Oh wait, I didn't turn off sound isolation. Again, sorry. I've been doing this is like the third recording, so please be patient. So R3 usually returns the values. Again, don't change too much with it. I mean, you can somewhat use it, because I use the return values a lot of the time going to be changed right before a function ends. So you can like somewhat use it more than the R4 to R10. But again, if you can use R12, if you really need multiple registers for your Gecko code, use 13 from Cherry 1. Sorry. I got it wrong. If you can, try to only use R12. If using only R12 is not possible, use R12 and R3. R0 is also very good for this stuff. So because I don't know how to explain this well. It is for temporary stuff. Like it is less mutual than R12. Again, heavily recommend using only R12 when evenly possible, but R12, then R0, and then R3. 3 is when it starts getting somewhat dangerous. And if you for some reason need 4 or more registers, again, if for some reason you cannot stick to only R12, R0, and R3, again, R3 should be kind of somewhat dangerous. So, if possible, only R12 and R0. But if for some reason you need to use more, that's what R13 to R31 are for. But again, I know I'm sounding like a broken record here. Try your best to limit yourself to the registers that will affect the rest of the code base. Because with assemblers, sanity checks are less common. It can do an operation with a control register, which I'm gonna say what that is later on, and branch to an invalid memory address and just crash the game. So again, be extremely careful. R2, this page I found says it does magic, and it handles multi-threading, which it might as well be magic. Do not touch R2. R1 is a stack pointer. Wait, is that stack pointer? Let me check something. I think R1 was the heap pointer. Isn't there a SP here? So SP is, oh wait, I think the SP and R1 are the same. So R1 and SP, you may sometimes see them be used interchangeably in some stuff. I'm pretty sure they're the same. I got confused. Where's the heap stored then? I know it can store just an address to a heap. Anyways, we're not talking about the heap here. The stack is a normal memory, all of that stuff. It helps to keep track of stuff for the computer. Which, that's another way of saying, do not touch it. R1 and R2, do what you do. never touch this stuff. Let them be happy. Never do anything with this tool unless you really know what you are doing. If you're just doing a normal code for like a ROM hack or something, R12. If you really need R0, if you really need to use multiple registers, you can also use R3. From that on, R13 to R35, to R31. If for some reason that isn't enough for you, you can dare to use this. Heavily recommend against that. And you can also use it. And from that point on, you run out of registers. I don't know which Gecko code you are making, but it's like more than 27 registers. If you need more than 27 registers, that's probably an issue with the code itself. You can be very good at simplifying codes, remember. Again, using this as an example. These early registers here that I told you to not use is because I'm moving. How do I explain this? I'm making space, pretty much. Because I want to do some funny stuff with branches, which I'm gonna explain in a second why you may want to just move instructions from the normal code to a C2 code. I just did this to create space. These aren't my instructions, these are from the game. I just move them from the normal place to wherever the C2 code wants to put it. But my actual code is this. And if you see, I load the address into R12, which I know I have said this multiple times. I'm going to explain what addresses are later on. Then whatever is in the address, I load it into R12, and then I compare R12 with immediate. When I was learning when I was just learning assembler, for some reason I threw R14 and a bunch of this a lot of the time. And that's a huge mistake. Sorry, I got lost in my train of thought. And that's a huge mistake. If you can only use R12. I know, said like 1,000 times already. It's like really important that you understand this. Because if you use some of these registers, again, these are safer to use than this, for the record. Another part of the code may call them, an issue may happen with them, and your code may result into a crash. You may have unexpected glitches, which glitches can be fun from time to time, but most of the time they're gonna crash your code. I'm drinking water, give me a second. So I think I already dance around it a lot. Memory addresses are what they sound, memory addresses. Address is a part of memory. Very literally, it's just the name of a part of the memory, to put it in a way. So like, here is the code has to be stored in memory, in which part of memory is stored in this memory address. I don't remember why it's handled like this, but in the WII, and I think in other PowerPC stuff, the actual use memory addresses start with an 8. Why? I have no idea. That's why I said earlier on that it's very important numbers that start with an 8, because that means that it starts with a memory address. Furthermore, if it's a register storing a memory address, or in some cases a memory address storing another memory address, I'm gonna get into how memory works more detail later on, it's what we call a pointer. A pointer, and I know this is gonna sound shocking, points to stuff. And this is a pointer because this is the stack pointer register. R2 does stuff with pointers as well. Again, it's multi-threading, so it might as well be magic. So this points to stuff, pretty literally, and does the stuff where it's pointing at. Let's go with more conventional registers that you might actually use, like here, this is a pointer. Let me check. I don't know, it's a pointer to something with sound. I don't know what the code was doing when I paused it. But pointers are important because there's a lot of instructions that do stuff with pointers. And just so you know, besides the storing code, numbers and other stuff can be stored into memory. I'm gonna go more detail into it later on. But here, I'm loading a pointer into R12. And then here's a special instruction. Load the load word and stuff like that instructions. This load word and 0, the 0 was an offset thing that, again, if you really wanna understand the offset and stuff like that, search the documentation I'm gonna link below, because I don't have time to explain all the details. But this load word and similar instructions, there's a load to word, which loads and stuff to point of registers, they're very important because they actually allow you to use memory. So in this case, I'm loading a pointer to this memory address. I'm gonna... Hey, I was working with it. Literally, right before recording it, I was working with it. This is the memory address I'm working with, which is an empty space, a 000. And what I'm doing here is that I load a pointer that points to this specific memory address. And you can notice this because if you go here and type it out, it will put you there, even if it says that is another stuff here. This is the memory. This is the 88 memory address. An 88 memory address. So what I'm doing is first making R12 point to this location in memory, and then I use this instruction to say load what is in the location of memory in this address. Well, actually, because of the zero stuff I mentioned, it actually loads whatever is in the address that this is pointing plus this offset. Again, the offset is 0, so the way this works is it adds 0 to a pointer, so it pretty much loads what's here directly and load it here. So in this case it's 0. So what I'm making here is that I load the pointer, then I say whatever is in that pointer, load it to register 12. So in this case it's 0. So I'm loading whatever is here to register 12. Or in other words, I'm loading 0 to 12 and then I'm comparing it with 1. Obviously, you can change memory later on. There's an instruction that directly loads stuff into memory, also using a pointer from a register. So you can start thinking why this is very useful, because you have limited register and all of that. You have a function that loads something into a spot of memory, and then you can load it. Be very careful with memory. You have limited memory. You should be using the heap. For reasons, I'm not gonna use the heap, but it's recommended to not use this space of memory the way I'm using it, at least, even if these spaces are always 0, because it's very likely it will make your codes incompatible with other codes. Actually, I usually use a lot of these spaces because they're 0. And you may be asking, why aren't you using this? Which all of this usually stays 0. All of this usually stays 0. I could be using this, but that's because I want this to work with other codes I have made. So I'm using different spaces in memory. But if you want to make like just a silly code that works a lot of stuff, do not use memory like this. Like, be very careful with memory and try to use this memory as possible, because it's very likely will make your code incompatible with other codes. And there may be times that the memory address says at 0, but then there's something else somewhere in the code that's barely wrong that uses it. It can throw off your entire code. Like, for example, my deadly star code uses this position memory. By the way, if you wonder why I'm using this one specifically, that is because I wanted to be compatible with the start scaling you code, because I'm using them both together for something. So something will be. So if something in the game, be it another code or a part of the game I didn't know about, loads any number here, it will kill Kirby. Well, it will kill Kirby with the code I'm using, which, by the way, is why we were. Oh, this was the pointer, right? Oh, this is another stuff. But like, why I was checking the subroutine is because I wanted to that subroutine runs every frame. Or what the code pretty much means is that it loads something into memory. If that something into memory is greater than 1, it kills Kirby. So if anything else in the game, or another code made by someone else, uses this address in the memory and my own star code, it will kill Kirby by accident, which, you know, can be a pleasant experience. Sorry, I'm kind of lost my train of thought there. We had an unpleasant experience because, well, you know, having the player just die randomly is not good for game design, last time I checked. So anyways, going back to the talk, now that we know what pointers are, more or less, we understand first what these registers are. Secondly, we will understand what other special registers are. Like the LR register, which is I don't know why I always lose the LR, this one, which you may have seen an instruction called BL here, which is different from just B. B is branch. As literally as it sounds, it just moves the place the code is looking at to another place. Then there's BL, which is called branch to link register, which it branches, but it creates to a pointer to a place it branch from. So for example, when this instruction is run, it will create a pointer to this memory address, and will store that pointer in this special register. And then branch to wherever it is. And then when this instruction is made, or I already moved, or another couple that like that, BLR is branched to the pointer that's in the link register. It will branch back. So most function calls use branch to link register. Like you branch to link register to a function. The function usually ends in a BLR, which, well, you see here, it's how it ends. So when it ends, it simply branches back to the place that called it, and that's how functions work in assembler. Usually, there are exceptions, like some have just normal branches. And remember, most functions still end in BLR. So this does not only branches to another function. When the BLR of that function is met, it won't go back here, because this is not a BL. Will branch back to the function that branches to this function, if that makes sense. So like, there's a BL function that branches here, and then this branches normally to another function, and that other function ends in a BLR. So we branch to a function that branches to this one, not to this function, like most functions. I know it sounds confusing, but we will get the hang of it. Why I describe anyway is kind of an edge case. Most functions simply have a branch to link register to them, and then they end in a BLR, branching back to whatever called them. Oh, wait, skip over this. These are floating point registers. If you want to be technical, they are double precision points. If you have worked with Java or C++, you may have heard of doubles. The PowerPC architecture, all floating point registers are doubles, and the way they handle normal floats by splitting the register into two, which we can see being done here. So they're weird. That's the best way I can put it. Floating points in hexadecimal or in assembler or anything like that are pain. They are not going to be very fun to use, especially because in PowerPC, each floating point register either has a double or two floating points. So there's a lot of weird management of using the upper part of the lower part of the register. And floating points are weird. And making codes with floating points is also not very fun. For Kirby, hitboxes and a lot of stuff are sadly managed with floating points. You have to somewhat use them. And a very good tool for them, which I forgot to put here, is a hex calculator, which... Oh wait, here it is, funny. Sorry, not a hex calculator. Why did... Well, a hex calculator is a very good tool, because everything is managed in hexadecimal. So a hex calculator is a good tool to have anyways. But there's an even better tool with a hex to float, which it's take a while to load, because Chrome, things like that. Let's wait for it to load. This will let you use floating points in a reasonable manner. Why do I say reasonable manner? Because, well, what is this? Like, floating points are very unintuitive compared to normal points, because any hexadecimal you can understand normal numbers. Because of the Matisse and a bunch of stuff I'm not going to explain here, floating points are very confusing in assembler. So I recommend trying to avoid them. But if you really have to, a floating point calculator, I'm going to try to link this alongside all of these other resources, which are very helpful. I'll try to link this below, because floating point calculators are excellent to making floating points actually usable. They're not excellent, they're pretty much required to actually using floating points assembler. Anyways, I'm kind of getting into that tangent there. This is why I don't record videos with my voice that much. And most of these we are never gonna use. I'm gonna go over the most important ones and some uses. Like link register. You are never gonna manually edit it, because first, you are usually not gonna create actual functions. That's very rare thing to do in assembler. In Gecko codes. But if you do, it's gonna handle it for you. Branch to link point register, it puts the number here. PLR, it returns to here. So you aren't really using this. What this is very helpful for is to copy it. I forgot which part of the code we paused in. And paste it here. Wait, what? Paste it here. Because it will return us to the last branch link register. Or in other words, it's gonna show us the previous function that was called before the function the game is previously called in. So if you wanna see, for example, the entire process of how the game creates a specific object, like a projectile, for example, you can pose a function you are interested in, for example, the constructor, you can put a breaking point, and when it pauses, you can go to the registers here, go to the link register, and see which function calls the constructor, probably a manager. And what else here? I forgot what some of these are because, again, you're never really using this. If you're doing some very specific stuff, you first probably already know more than me. Secondly, you probably already know what these are, so like, if you are interested, do more research into this. But besides, there was another useful one here. Like, a bit mask is for, how is this thing called? For saving them. Like, bit masks are very good. Like, these masks can be very useful for some stuff, but again, most of these are beyond the scopes of this tutorial, because I just only want you to get the basics. So you're gonna really use this for most of your code. You're realistically only gonna use this little guy over here. If you need to use floats, you're gonna use the floating point registers. There's some edge cases, especially when Mint is involved, because Mint is an interpreted language, and interpreted languages makes a lot of this more complex. Like, remember this chart here? Mint or Basil, however you wanna call it. I mean, it's made for Return to Real and Basil for future games. Because Mint is an interpreted language, it's run by other program. Another program is the program itself is the one that understands the Mint. There's a Mint grabber function, and if you are interested into it, you can see how Mint's handled by the code. And because, again, it's pretty much reading other code and then running functions from there. That's like the simplest way I can explain how it works. Mint functions can be very complicated, and the issue with Return to Dreamland specifically is that there's this thing called action states. Unlike future games that use Basil or Mint 2.0, I think is the one that handles everything from Mint. Return to Dreamland has kind of a hybrid approach to it. On one hand, you have just direct compiled code. So like, for let me take a more specific example. You are doing the fireball attack of the fire, or boarding, I think is how the game calls it. You're doing the boarding attack, which for those of you who don't remember is when Kirby becomes a fireball and moves. I will search it again, this lags my computer a lot. Because of the weird way Return to Dreamland was made, the moving part and the projectile spawning, if you didn't know, if you press 1 while doing it, you will spawn a little fire bullet. That's handled with assembler, but the effects of like turning Kirby into a fireball and all of that, that's handled by Mint. And it becomes really problematic because first, more action state is complicated, to say the least. But secondly, there's a workaround for it, and no, this is not the one that uses the workaround. I think the first person to come up with this workaround was Dudelook. Let me think. Let me find one where I use it. I think it's a normal attack, the one I use this workaround. Let's wait for it to load. My computer's a little bit slow, but I'm sorry. Probably already noticed it is. But this is getting into very specific Kirby stuff. If you are here for the normal assembler tutorial, feel free to skip. It's not this one, I think. It's not this one. Let me find it somewhere here. It's not shopping, it's the one before shopping. Spin? No. I It was attack, I'm pretty sure it was attack. Let me open this again. It would be very good if it loaded. I remember marking the custom code part, but let me search. Maybe I forgot to mark it and just left it there. So there should be like a jump somewhere here. This is for the Firestorm mode, by the way. Oh, I'm an absolute idiot. This is the vanilla one. So it was somewhere here. The one I actually use. Yeah, it's this one. Scene, step. Sorry if the tutorial is kind of slow. What do you expect from an assembler tutorial though? This is the one I edited. So here's the issue. Mint handles hitboxes, effects, and similar stuff. Here's the custom part I made. And because adding new action states is borderline impossible, I mean, not impossible, it just takes a lot of work, and why bother? So what Dude Luke, I think he was the guy who came up with it, find out is that you can simply check for which button the player is inputting, or for above you can just do a call to randomness. And here it is. Here it is checking, if my memory doesn't fail me, if the player is holding down. If the player is holding down, it jumps here, it jumps to here, and it does another custom attack. Here specifically, if you have seen the Firestorm mode, this is the part that essentially adds the new attack where pressing down on one creates a little fire instead of attacking normally. But there's an issue with that, at least for me. That still has the sword projectile when you have full HP, because projectiles are handled by assembler. So this is one of the edge cases where that's probably gonna make the game crash. But you know what I did there? So this is one of the edge cases where you will actually have to use this stuff. Because for some reason, again, it uses a grabber, if I'm using me. Tell me, I think, I don't know if there's a full-out parser for Mint, but it uses something like that to handle the main bytecode. While handling the main bytecode, especially if you are telling it to different stuff, what is left over, to say it like that, in some of these registers, especially in the floating points, maybe different from function to function, so like, something I found out, it was some weird stuff, like floating point register 9, for some reason. Ended up having a different result when I did the sword attack normally, and when I did my custom version of the attack when I pressed down. For some reason, it ended up only this register, like all the other ones were the same, but for some reason, only this one was different, depending on the way I run them in. So for some reason, it was different, so what I did is I made a compare instruction that checks for this, and if this was a certain value, it will do a normal sword, it will spawn the projectile, and if it was another, it wouldn't spawn it. That's how I made it so you could do the down attack without spawning projectiles. So, especially with Mint and other programs that handle interpreted language, and other games that have interpreted languages, you may have to do some weird stuff with registers. To interpret the languages are weird. That's why I really don't recommend using them. But besides the edge and weird cases like that, stick to general purpose registers. A lot of stuff you do with floating points, you can do with general purpose registers. You can handle decimals by dividing them. I mean, not really, like just imagine. Yes, but no. And you don't want to use decimals anyways. For most stuff, decimals cause errors. So, well, there's that. That's all the registers you want to know. I think the next thing, let me check my notes here. Next thing I wanted to explain after registers. Oh, I wanted to explain functions and pointers now. Well, I already explained pointers, so let's explain a thing about functions. Functions themselves, you probably already know what they are if you use Mint, if you use literally any programming language. It's a block of code. And in assembler, is that literally. It's just a chunk of code that you branch to with a link register and that you return from. What's the catch though? It's not a catch. It's an interesting thing because if we go here to simple, to our symbol map, there's this thing called a symbol map. Usually, this is a tool for game developers, a debugging tool, that says what everything does, in case, maybe you have to check the assembler or something, or there was another use for it I forgot, but pretty much says what function is part of the code. Because imagine coding without naming functions properly, it will be hell. Each function is pretty self-explanatory to what it does inside the code. I said code twice, oh my god. This tutorial is a mess. But anyways. Because each part of the code is usually named after, each function is named after what it does. Knowing what functions are pretty much tells you what everything does. I already showed you the example, let's go back to it. What? Yeah, I forgot. Let me go back to this one. It sounds like you need some knowledge of the game to really understand it, but this is a create function, so it creates something, especially when you see here that it's branched into a constructor. So more than just creating, it is a function that starts the declaration to create an object. CT means constructor, by the way, which, how do I explain that? If you know object-oriented programming, constructor creates object, and object is a data structure. DT, the structure, it destroys the object, pretty much. You see, a state factory arc. A state factory is what I call action states, which in Kirby specifically, each attack is an action state, jumping is an action state, falling is an action state. So it's pretty much all actions, because the way the game works, both Kirby, the enemies, and the bosses, which are 3 different types of entities, bosses are different from enemies, all of them use a similar action state system to kind of like that. I mean, there's all the differences, but all of them use action states. So when you see a state factory is, well, it's straight in a state. There's util I state, this means that it's in the utilities functions. CNN, which SCN, which means scene, I don't know what to cover me there. For step hero nanana, if we see the mint again. Well, sorry. We see scene, step, hero, common. There's no anime script here for some reason. But common, state hover, and then a bunch of stuff that says hero, by hero means the player characters. So hover, this is one of these. Where was hover again? Here. Is this? I remember each action state has a mint and a compiled code for a C part, I guess. So it's pretty much that. That's like there's no much of it that's that complicated here. Like we know it's an action state. We know it's from the hero, and scene is pretty much where action states are stored. So it says state factory, and scene is pretty much an action state. We know that say hover is when Kirby flies. Ignore this is a custom code, don't get confused with it. Let's use this as an example because it's better. This is when Kirby shots the air puff after he ends flying. So we know this is the function that creates the air puff. But there's a thing. How do we know this? To be more direct, why do we have this here? Because if you're a game developer and don't want people hacking your game and stuff like that, you usually don't leave this here. This is why I said, I mean, besides the plenty of examples with Return to Dreamland stuff, why I said this is a special thing with Return to Dreamland. They left the symbol map. This is a walking tool. This should only exist for the developers. I don't know what happened. Probably an accident. If I have to guess, someone probably got fired because of this. They left the entire symbol map in the game. And this is not the first. And this is not the only time HAL has done something like this. So because I don't know how that happened, but because in the game files, literally in the root of the game files, someone just casually left the entire symbol map, we now have pretty much access. Well, not access. We pretty much are able to tell what each function in the game does. And that already helps a lot, because with some basic knowledge of assembly, that I hope this tutorial will at least give you some of that, of like what a compare is, what a branch is, that when it says back is branch if the result here is equal, with what's an addition, that if you don't understand something, you can simply go here and, not here, go here and search for it or Google it if you have luck. I have very bad luck Googling. I decided to brave in, I guess. I hope that with what I have explained to you, you are able to at least get some basic grasp. I forgot to mention this, by the way. If you, for some reason, wait, what? Drink some water. Wait. Okay. Sorry. I got lost track of stuff because I got a message. But anyways, there's a thing I forgot to tell you. Is that there's this replace instruction thing you can do in Dolphin. This gives you the machine code equivalent of the instruction, which is, you see, it's pretty much this part of a code. This helps you for two things. First, you can just replace it. So here, you can get like an instruction from here. I'm not gonna run the game anymore after this tutorial, so it doesn't matter. You get this random instruction here, which this one is this one, this one is this one. So it should be the third. It should be this. You could get this instruction, which is this one. You just put it here, and this is probably gonna crash the game because I just got a random instruction. But you can replace these instructions. Let's do it again. Let's put the compare instruction because why not? Again, probably it's still gonna crash the game. And you see, you can replace instructions for where you want. This is very helpful to test gecko codes on the fly. Because now we're getting back to the topic of gecko codes. These gecko codes, you have to pretty much get them, copy paste them, go to properties here, have the gecko code stuff, scroll down, create a new one or edit one, or like edit one or something. It takes a while, especially because to run the gecko code you have to run the game again. If you want to just test a change to a part of the game code on the fly, you simply check what an instruction compiles to, which is something you can do directly. Like, let's delete one, I already saved it. You want to, I don't know, load something into register for some reason. 6 into register 4. See, oh look, this is what this instruction is. I just do that to search for a specific instruction and then just replace it. Look, we have put load 6 into register 4 into a game code. A random part of the game code that's probably gonna make it crash. But doesn't matter, this is just an example. Wait, what is this for? What's this for again? Is that here? Ah, it's hover. This is probably gonna crash the game whenever you hover. But anyways, let me check my notes. I lost them. That's great. Functions and memory and pointers and oh Christ! I forgot one of the most important stuff. Because I say to code, that you say it takes quite a chunk of space. If you ever want to, how to explain this? It doesn't only take a good chunk of space, but it's minimum. It adds 2 extra instructions: a branch and the branch back. You just want to replace the instruction directly. You can see how the instruction is written. You can copy the address. I actually want to see what happens here. Little experiment time, I guess. You can copy the address you want to replace. you replace the 80 technically, not an 80, but whatever. You can replace an 80 with a 04. And then next to it, let me get that. Replace instruction. But let me find this. Sorry, I've been recording this for multiple hours. Sorry if I'm not sounding the clearest. And most of these writers are made for C2 codes, so they will understand it. But these are code that simply replaces. It was 94, right? Why are we here? That. Wait, sorry. That replaces whatever is in. Sorry, I got confused. That replaces whatever is in here, so here, with this instruction here, which will be the equivalent of doing this by the code. Oh my god, that's the zero buffer address? Lol. The branch directly to it, that's funny. Anyways, I think I explained that poorly. If you just want to replace a single instruction, you copy the address of the instruction, replace the 80 with a 04, and then replace the machine code of whatever that instruction is. If you want to get the machine code of an instruction, simply load up any of these assembling tools as your assembler to code, I guess. And here, if you see to code, you can see that the instruction is very clearly here. You can just copy paste that here, and then do the rest I told you. You get the address 04, get this, and copy paste it there. And C4 codes are, they're not necessary, you can technically do the same. With C2 codes, they're simply more efficient at replacing individual instructions. And now that I remember, if you want to branch to your parts of the code, you have to do stuff like 04 codes. Because unless you want to use control register, which I forgot to mention in the register parts, is this one here. You cannot, all branches are done with a direct amount of spaces. And the issue is that C2 code finds any space in any free space in memory, just drops it there. So C2 code is unreliable. So you will usually have to use C4 codes for stuff like branches. And that's where you get into stuff like making space by moving other parts of the code to C2 code and all of that stuff, which is what my code that was here did, but I deleted it. And so C4 code, 04 code, very important. First, when you just want to replace a single thing and want to be efficient about it. Secondly, if you want to have a branching. Because you can branch within the C2 code, but you cannot consistently branch between a C2 code and a part of the normal code. So you want to have branches within the normal code. You have to replace, you have to grab the address of an instruction, replace it, and replace it with a branch instruction pretty much within the code itself. And to prevent it from causing issues, usually you can just make a C2 code and move parts of move stuff like normal as instructions that are no branches. That's why I want to make it clear. You cannot move branches to C2 codes. If you want to make space for something, usually for branches, you can move normal instructions to C2 code and then have a branch later on if you want to branch within the normal code. What's next? Jesus Christ, I've been doing this single recording for an hour and a half. No wonder why my throat wants to kill me anyways. Memory. Memory breaking points is the next thing. I already kind of explained it, but just to say it again, I repeated a lot of stuff already anyways. This is memory, there's a heap and stack. How do I explain the difference? Like, if you know C++, you probably already know the difference between a heap and a stack. But you probably do not know C++. If you're listening to this. So, there's this thing called dynamic memory. There's the stack. The stack is where most of your memory is, and is why you have a pointer to it. If I remember correctly, you could also use this pointer for the heap, because if my memory doesn't fail me, the heap and stack sometimes mixes, so there's some weird stuff you can make to access the heap from here. But I do not remember the exacts of it. And that's an interesting thing, because you are not going to use memory management most of the time. with a very few exceptions, you are not gonna use memory management. I just say I don't recommend doing it. Just find an empty space in the stack and use it. Like, it's not proper programming practice, and if you wanna make a Gecko code that's compatible with more stuff, take the effort of learning what the heap is. But the heap stuff is complicated. I have already been recording this for an hour. Counting previous attempts, multiple ones. So like, if you really want explanation of the heap, I know this is gonna sound rude, search it yourself. Because heap and low memory programming is complicated stuff. Like, people have memory lakes and stuff in C++ and high language programming. Imagine how much of a hell this manage the heap from fucking assembler. So, because it gets complicated, I'm not gonna get into the stack and heap stuff here. I'm just gonna say that there are instructions that using a pointer in a register can load stuff into memory, and you can load stuff from it. For serious codes, it's not recommendable doing it. For stuff that you want to be compatible with other codes, it's not recommendable doing it. But if you know that nothing else is gonna be used with your code, or if you are making a ROM hack and are an asshole or something, I don't want other people using codes within your code, you can also make it this way to make it crash in purpose if someone's trying to cheat in your ROM hack. I don't know why you will do that, but I guess you could do that. But anyways, let me drink some more water. Anyways, that's really it, because like, unless you want to get into specific stuff, the memory is just a place where you can put numbers that stuff registers, and you access to specific instructions that handle the memory directly. Let's go to the instruction set book again, and load word. What I like with this book is that it has a lot of tables. Let me try to find a table. Do you have one with a minute? No, you do not. Because you're loading a word from memory. Why would you use an minute for that? But like, let's ignore the table. Like, I already show like a couple. All of the instructions I'm showing load stuff from memory. Which one was the one that loads stuff from memory? I actually had it here. Give me a second, please. So usually, if it has this, it loads stuff into memory. And I had the same code, actually. Ignore the name. I'm not working in any projects right now. I think this one is the one that loads the stuff after you do a phony. This code is gonna be very fun for people. That's what I'm gonna say. Can't wait to show it off. It's gonna take a while, because I don't have any ROM hack at this point. Anyways, a store word. That's the one I'm searching for. Or with memory, that's most of the stuff. I mean, there's like some niche stuff, and I recommend you, if you are interested or want to work with it, to look into it yourself. But for most stuff, you're gonna only use LW instructions to load a word from memory, or you are gonna store stuff from memory rarely, because it's not recommendable to do it, even though I just showed an example of me doing it. Do as I say, not as I do. Anyways, memory breaking points is how to explain this. Memory breaking points is why this menu exists. How do I explain this? With this menu, you can create breaking points. You can create code and memory breaking points. But if you remember what I said earlier, you can simply go to a code and bam, breaking point. And this is simply more efficient to do. Like, this is good to keep track of them and manage them, but you can just bam, breaking point. Like, you can look at the code and put the breaking point there. Like, bam. This is way more, how do I say it? more smooth to work with. But with memory has a lot of funky stuff. So I do recommend using this for memory breaking points. An instruction breaking point is the ones I just show in the code. A memory breaking point here is... Well, this is a memory breaking point. How it works is you copy the address. Again, you know what? Let's use the code I made here. You copy the address to a memory address, and you have a condition. As I told you earlier, you can store words. I don't know why there's branches here, but store words and load words. From the computer's perspective, that's pretty much reading from memory or loading into memory. Or writing into memory is how the term is called. So you can put a breaking point that only stops if a certain position in memory is read. In this case, if this position in memory is read by a load word instruction, it will pause it, but if you are writing something into it, it won't stop it. You can do the opposite of if a store word instruction is run, it will pause it. If a load one is run, it won't stop it. Or you can do both. And there is some stuff with logging, which like it only really matters if you have both. Then more to keep track of it if you are working with something. I mean, it's logging. That's what logging means. So, but yes, I don't know how to say this to log stuff. And there's also ranges, which I also think is pretty self-explanatory. Now instead of just being a breaking point in this address, there's a breaking point if anything happens in this entire area of code. It is very useful for structures. Data structures are usually, especially if they are stored together, so you, I don't know, something changes to a stroke of Kirby, I don't know. You want to always pause whenever that's changed. Then you can have a write or write and read, I guess, if you also want to check that. In entire range that where the struct is stored. So, I mean, yes, there's like not much to say about breaking points. You can put breaking points that only stop when memory is being read, some when it's being written, some when it's being written or read too. Sorry, I forgot the regular verbs are a thing for a second. There's an instruction breaking point with that can also have conditions, but again, with instruction breaking points, most of the time, all you need will do is bam, 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 bam. I personally only really use this menu for memory breaking points. Before finishing, there's a thing also related to memory. If we go to emulation, it was somewhere. I forgot what it was. Oh, well, that's because I don't work with memory that often. But if you wanna know where something is stored, there's this tool called sheet search, and I know there are some add-ons to Dolphin that are more efficient at this. But it would be beautiful if I found it. Tools, I think it's here. Sheet manager, is it sheet manager? I think it became sheet manager after an update. Yeah. Here it is. This is a modern sheet search. When I started doing this, it was sheet search because it was another version of Dolphin. There's a lot of options you can do. If my memory doesn't have this custom address space, like I'm not sure what it means, but my thing means is there if you are using a mod or something that expands the memory of the Wii. Well, the game, because again, it's an emulator. I think I'm not sure there. Yeah. I forgot how to read for a second. So this is if you want to make a Gecko code using if you are searching for something only within the memory of the Wii. This is if it's like this works for first some weird extra stuff you can make with Dolphin and mods, and because it has a range. Because you can also set a range, you can also use it normally to only search a specific part of the code within the game's normal stuff. Again, I'm not sure about the custom stuff. I may be confused with another thing. But you can, but even if that is a function, again, I may be confused. This also works to search a sheet, search a space of memory within a specific in a specific range, which you know how it calls it. Well, again, it's self-explanatory. Start of range, set here. End of range, set here. And what else? I really hate this change. You will be able to change this on the fly, but this is how you wanna have the data to be seen and computed. How do I explain this? Technically, all can find kind of mode stuff, but it's difficult to explain with memory. In memory, you have this display thingy. You can change it to multiple forms of display, and it will show you the memory, the parts of memory, in like how I explain different units. I guess there was probably a proper name that I forgot. They're like fixed alignment. There's a lot of stuff that again I don't deem to be that relevant. Because I personally just stick with hex32, but if you are searching specific stuff, again, that for the sake of completion I would say it, you can have different options here to change the view range of how it will space the code. Sometimes that is more useful for some better specific stuff, but I stick with hex32. Also, wait, I'm gonna get into that later on. I stick with hex32 because when you set a value here, or more importantly, you're using a store or load function, usually it's gonna load in this order. Like when you load that stuff from memory into an address, it's usually gonna load all of this number. You can change that with offsets and a lot of other funky stuff. But with hex32, but that's it. Hex32 shows how things are gonna be loaded into a register, the base. So I recommend sticking with it. If you're searching for specific stuff, feel free to change how it is split in the numbers. This one can be particularly useful when you remember that a lot of stuff in assembly is only loaded by half and half, so I guess if you want to specifically remember how to load a pointer part will getting confused, hex16 can be useful. And in niche cases, you will find uses for this. By my experience, I stick with hex32 and it works pretty well. What else? Oh, I never saw that shit. How to explain shit search? I'm trying to think about it. Okay, shit search is to search for specific values. If you want to learn how to use the tool, in most games with 1-ups, your lives are going to probably be the best way of searching it, or in most games with... how is this thing called? I forgot the name of it. HP values are exact, it's an RPG I guess. This tool can be very useful for searching exact values. If you want to know where the player HP is stored, the game has direct HP. You can simply search for the value of HP. Let's say, again, I'm not running the game because it will kill the recording. I don't want to lose an hour of recording to that. So for example, Kirby has 4 HP in normal mode. He has 28 in extra mode, just to tell me. Display hex values, you know, again. I will explain everything because like display hex values means that it's going to display hex values. And you put this value, or you also have the options of vary it to the last value or any value. I don't know how any value works exactly, it always confuses me. And then you can search for a condition, if it's equal, that is equal, not equal, less than or equal, and you can read. These are the options. And you compare it. And when you search and filter, which I won't because it will probably kill my recording, my computer is a potato, as I have stated multiple times, will give you all the locations in memory that have 4 is sort. And again, this is why this view thing I explained earlier matters. Because if you have hex 16 or something like that, if there's a 4E here or a 4E here, it will return you the addresses to those locations. And because of the way the game works, usually most numbers start in a base of hex 32, if that makes sense. Like, if a 4 is the sort, it's gonna be stored in the lower part of the memory address of hex 32. I hope you understood what I said there. And again, you can search a lot of stuff with this, especially because the point of cheat search is that you can search for a memory location while playing. So for example, you're playing with Kirby, you know the base HP value is 40, even though, yeah, it's 40, it's the story param. Param, you can change it to whatever, it will be the param value anyways. And you like take damage. So you set this to, it's less than 40, because you just took damage. And you search again. Sorry, okay, give me a second. Search again. The results of the previous search are still going to be there. So like, let's give a very simple example. It's usually gonna be like the 1000 or something like that. So like, let's say that 1000 addresses, is arguably gonna be more, told you that they have 4 HP. You then took damage. And you search this list. It's gonna compare that it has less than 40 only within that 1000 addresses. And you can do this multiple times, and you can start seeing how this becomes useful. Because you can start, well, the name is here, you can start filtering down by playing with the value until you find the specific memory address you want to change. So in this case, you want to like take damage again or heal again and check if it's equal to, and like do that multiple times until you find the memory address. Until you find the memory address storing what you want. So yeah, that's how cheat search work. Very useful for finding specific locations within memory. Well, that's pretty much it. One last thing is check all of these resources. They are very good. And that's about it. I have taken hours of this, so I'm ending this now. If you want me to make more of this, tell me, and I will probably